with Mr. Thomas.
Hello again! Chapter 6, Lesson 11, MacLaurin Series 2. More MacLaurin? More MacLaurin. In the last lesson we were looking at MacLaurin series and I introduced you to what it is all about and gave you examples 1, 2, 3 and 4. What we're doing now is starting with example 5 and we're moving on to look at some of the harder examples. If you are still unsure about the MacLaurin series though, you are best going back to look at the first set of examples. Example 5 with MacLaurin series. Part A, obtain the MacLaurin series for the function f of x equals e to the power of x sin x up to and including the term in x to the power of 4. And B, hence obtain the MacLaurin series for the function g of x equals e to the power of 2x sin 2x up to and including the term in x to the power of 4. You already know from the previous lesson, in order to express your function as a MacLaurin series, you have to differentiate it. So we need to differentiate f of x. Differentiate then e to the power of x sin x. What would we use? Ewan? Product rule! Perfect! You would use the product rule. And why do we use the product rule? Brilliant, because it is the product of two functions. You have a function in terms of x multiplied by another function in terms of x. So the product rule. U dash v plus uv dash. U is going to be e to the power of x and v is going to be what we're multiplying it by, which is sin x. Differentiate e to the power of x and it stays as e to the power of x. Always remember to multiply by the derivative of the index, but if you differentiate x you get 1, so it would just stay as it is. Differentiate sin x and you get cos x. Therefore, f dash x, u dash v plus uv dash becomes e to the power of x times sin x plus e to the power of x times cos x. From there, you have to differentiate once again, but because you have a product here and another product here, you'd have to use the product rule twice. To make it easier, what could you do? Good, look for a common factor. The common factor here is e to the power of x. So, you have e to the power of x times the sin x plus cos x. It means differentiating this rather than having to use the product rule twice, you can just use it once. Because we've got an e to the power of x, so that is going to be u, and we're multiplying it by sin x plus cos x, so that will be v. Differentiate u dash will be e to the power of x, and v dash, if you differentiate sin x plus cos x, you get cos x take away sin x. Therefore your second derivative, f double dash x, is u dash v plus uv dash, which goes to e to the power of x times sin x plus cos x, plus e to the power of x times cos x take away sin x. From there, because really we're wanting the term up to and including the term in x to the power of 4, it means we're really looking for this fourth derivative, so we have to keep on going and differentiating. If we differentiate this again, well, you'd have the product rule here and you'd have the product rule here, so you'd have to use the product rule twice. So again, look for common factors, or maybe what's even easier for this bit is if you multiply out the brackets, which is what I'm doing over the page. If you multiply the brackets, you get e to the power of x times sin x and e to the power of x times cos x, and the same with this bracket here. But the whole point in doing that is you have an e to the power of x sin x, and then you're taking away an e to the power of x sin x. And you're left with e to the power of x cos x and another e to the power of x cos x, which means you've got two of them. So you have 2 e to the power of x cos x. Same thing would have worked if you took out the common factor and then simplified. Just look for ways of making it simpler before you differentiate. Differentiating this then to e to the power of x times cos x, once again you use the product rule. Brilliant. And you use that because it's one function in terms of x times another function in terms of x. So u is going to be 2e to the power of x, and if you differentiate that, well, the 2 will stay as it is, e to the power of x will stay as it is, multiply by the derivative is just 1 if you differentiate x, so you multiply that by 1 so it stays as it is. Differentiate cos x and you get negative sin x. Therefore this third derivative, u dash v plus uv dash, is 2e to the power of x times cos x plus 2e to the power of x times negative sin x. Because I've got the negative, I'm just moving the negative to the front there. I'm putting the 2e to the power of x first, and then we're finishing off with the trig term. From there, once again, what would make that easier before you differentiate? Good, common factor. So take out a common factor of 2e to the power of x. 2e to the power of x is your common factor. It leaves you with a cos x take away sin x. And from there, once again, you need to differentiate. Remember, we wanted to include the term in x to the power of 4, so we want the fourth derivative. So if you differentiate this, you have to use you got it, it's the product rule. So u is going to be 2e to the power of x, and v is cos x take away sin x. Differentiate 2e to the power of x, it stays just as it is, and differentiate cos x take away sin x, that gives you negative sin x take away cos x. The fourth derivative, u dash v plus uv dash, it works out to be 2e to the power of x times cos x take away sin x plus u times v dash 2e to the power of x times negative sin x take away cos x. Once again, you could multiply out the brackets there, or you could take out a common factor. Doesn't really matter which way you're doing it. You get a 2e to the power of x cos x, take away 2e to the power of x sin x, take away 2e to the power of x sin x, take away 2e to the power of x cos x. Really, I'm multiplying out the brackets there. The reason I'm doing that is you can easily see that these terms will cancel. And these two terms, you can put them together. So you've got negative 2e to the power of x sin x. You're taking away another 2e to the power of x sin x, which means then you'd have negative 4e to the power of x sin x. So we have now found the fourth derivative. Woo! What do you do after that though? We have worked out the first, the second, the third, the fourth derivative. Brilliant. Now you need to evaluate each of these for when x equals 0. Remember, what you're really doing is, this is the formula for the MacLaurin series, your MacLaurin expansion. F of x equals f of 0 plus f dash 0x plus f double dash 0 over 2 factorial x squared, and so on. So after you've worked out the derivatives, you need to evaluate them all when x is 0. So you need to work out f of 0. So to do that, you would have e to the power of 0 times sine of 0. Work that out and you just get 0. Because sine of 0 is 0, this would be 1, 0 times 1, which is 0. Do the same thing for f dash x. So f dash x would be e to the power of 0 multiplied by sine of 0 plus cos 0. That there works out to be 1. Do the same thing for the second derivative. You would have 2e to the power of 0 times cos of 0. Cos of 0 is going to be 1. E to the power of 0 is going to be 1, so it's 2 times 1, which is 2. Third derivative, again, replace x with 0, evaluate that, and it works out to be 2. And for the fourth derivative, when you replace x with 0, negative 4e to the power of 0 times sine of 0 works out to be 0. Because sine of 0 is 0, so you're multiplying everything by 0, so that's all you get. After you have evaluated each of them and you know f of 0, f dash 0, and so on, you can sub them into this formula that is given on the formula sheet. So f of x was e to the power of x sine x, and we can express that as an infinite series, and that would be then f of 0 was 0, so that's just going to be 0. F dash 0 times x would be 1 times x. F double dash 0 over 2 factorial times x squared. Well, f double dash 0 is going to be 2 over 2 factorial, 2 times 1, so that's just 2 over 2 times x squared. Sub in the other values as well, and that is going to give you 2 over 3 times 2, which is 6, or multiplied by x to the power of 3, plus, and then that's going to be 0 over 4 factorial, 4 times 3 times 2 times 1, and that's going to be 24, multiplied by x to the power of 4. And remember, it is infinite, it's going to keep on going, so I've got plus dot dot dot. Simplify that, and really 0, you can get rid of that, you don't need to write it. It starts off with 1x, which is just x. 2 over 2 is 1, so we've got 1x squared. 2/6 is the same as 1/3, so we have 1/3 x cubed. And 0 over 24 is 0, so we've got 0x to the power of 4. So that there is our answer. Note, remember the question, it was saying to obtain the MacLaurin series for the function up to and including the term in x to the power of 4. Sometimes you will get this in an exam. The coefficient for this x to the power of 4 will be 0. But we have shown all the working behind that. We've got the fourth derivative. We've evaluated it when x is 0. So we know when we sub that in to the MacLaurin expansion that it is just going to be 0 multiplied by x to the power of 4, which means then you just have 0. So you don't need to write that. But we've got the working to show that we did it. That there is your answer. Part B. Hence, obtain the Maclaurin series for the function g of x equals e to the power of 2x sine 2x up to and including the term in x to the power of 4. For this, because this is a part B, most of the time for part B you're going to be using what you already know or what you worked out for part A. So in part A we worked out that e to the power of x sine x equals x plus x squared plus a third x cubed, and so on. How would we go about working out then the expansion for our e to the power of 2x sine 2x? Well, yeah, one way we could do it is you could do the whole thing again. Differentiate your e to the power of 2x sine 2x and then work out the fourth derivative, but you'd be there forever doing that. We need a better way. Perfect. If you look at it, all we're really doing is we're replacing the x here with 2x. So we're replacing x with 2x. So all we have to do on the left hand side, we've replaced x with 2x. So on the right hand side, we do the exact same thing. So we replace every single x with a 2x. So we're starting off with 2x. And then instead of x squared, we'd have 2x in brackets squared. Instead of a third x cubed, we'd have a third x 2x cubed plus dot dot dot. That is you're replacing it. You just want to tidy it up then, so the 2x would stay as it is. 2x in brackets squared would work out as 4x squared, and a third in brackets 2x cubed would be 1/3 times by 8x cubed, which simplifies again just to the 8/3 x cubed. And that there will be your answer. Notice again you are having to do that up to and including the term in x to the power of 4, but you know the coefficient was 0, so you would still be multiplying by 0, so you still don't have to write it. That there will be your answer. Example 6. Obtain the Maclaurin series for sine squared x up to and including the term in x to the power of 4. And B. Hence obtain the Maclaurin series for cos squared x up to and including the term in x to the power of 4. So to do this, we know that we are starting off with our function sine squared x, and we would have to differentiate it. So differentiating that then, we would have, well, to differentiate it, sine squared x means sine x in brackets squared. To differentiate, bring the power down, take 1 off the power, and then multiply by the derivative of what's in the brackets. Differentiate that, you get cos x. So we have 2 sine x cos x. What we can do from there is we could use the product rule, because we've got 2 sine x times by cos x. And if you use the product rule, that's absolutely fine. You'd have u dash v plus uv dash. And once again, after that, once you simplify, using the product rule again and again and again. However, there's sometimes little tricks, little ways that you can make this easier to differentiate. Does anybody remember what 2 sine x cos x is equal to? Perfect, Mary Lou waving her hand. It is equal to, well done Mary Lou, you're perfectly right. It is sine in brackets 2x. That is going to be a lot easier to differentiate that, because you don't have to use the product rule. So differentiate sine 2x and you would end up getting, well, sine, if you differentiate it, it goes to cos. So we'd have cos of, keep the brackets as they are, multiply by the derivative of what is in the brackets, that's 2. So you end up with getting 2 cos 2x. Differentiate that, once again, you don't have to use a product rule. Because we've simplified it here, we've made it so much easier for ourselves. So differentiate 2 cos 2x and you end up getting, well, the 2 is going to stay as it is. Cos is going to become negative sign, so we've got this negative sign. Keep the brackets as they are, so keep the 2x and then multiply by the derivative, which will be 2. Tidy that up and you get negative 4 sine 2x. Differentiate that, we are wanting to work out the term up to including the x to the power of 4, so we want the fourth derivative. So keep the negative 4 just as it is. Sine, if you differentiate it, it goes to cos. 2x would stay as it is, and again multiply by the derivative, so multiply by 2. Negative 4 times 2 is negative 8, so you've got negative 8 cos 2x. Woo! Once you have done that, you know you have to evaluate it for f of 0 and f dash 0, f double dash 0, and so on. Replace the x with 0. So doing that, if you work out sine squared 0, that works out to be 0. Perfect. Because remember, that is sine of 0 squared. Sine of 0 is 0. Square it, you still get 0. Sine of 2 times 0, 2 times 0 is 0. Sine of 0 is still going to be 0. For the second derivative, 2 times cos of 2 times 0, this is going to be 0, so 2 cos 0. Cos of 0 is 1, so that's just going to leave you with 2. Negative 4 sine 2 times 0 is going to be negative 4 times sine 0, which is going to be negative 4 times 0, which is just going to be a 0. And negative 8 times cos of 2 times 0 is going to be negative 8 times cos of 0, which is going to be negative 8 times 1, which will leave us with negative 8. So we have evaluated f of 0, f dash 0, f double dash 0 down to the fourth derivative, and once we have that, again, for the Maclaurin series, you know you're going to be using this expansion here. So your function is going to be f of 0 plus f dash 0 times x, and so on. So our function was sine squared x, that's what we started with. F of 0 is 0, so we are starting off with 0, plus f dash 0 times x is going to be 0 times x. F double dash 0 over 2 factorial times x squared will be 2 over 2 factorial is going to be 2 times 1. So that's just 2 over 2 x squared. Keep on going with that and you're going to have 0 over 3 factorial. So 0 over 3 times 2 times 1 is 0 over 6 times by the x cubed. And then you've got plus the negative 8 over the 4 factorial. 4 times 3 times 2 times 1, which is 24, multiplied by the x to the power of 4, and so on. You've got the dots. That is what you would end up with. Just simplify it though. You've got 0 plus 0x. You don't need to write them. So really we're starting with 2 over 2x squared, which just becomes 1x squared. This term as well would disappear and you would have a negative moved up to the front. So you've got the negative. 8 over 24 is a third, so a third x to the power of 4 plus dot dot dot. So that there is your expansion of sine squared x. Woo! Part B. Hence, obtain the Maclaurin series for cos squared x up to and including the term in x to the power of 4. Once again, because this is a part B, we are going to have to use our answer from part A. So in part A, this is what we worked out. How can we use that to find the Maclaurin series for cos squared x? Does anybody know what you would do? David, what do you think? Brilliant! You're perfectly right. You need to remember that sine squared x plus cos squared x equals, you got it, well done, high five. Woo! Which means then if you want to get cos squared x just on its own, well, you subtract sine squared x from both sides. So cos squared x equals 1 take away sine squared x. How does that help us here? Well, we know what sine squared x is equal to. So all we have to do for this is replace this sine squared x with what it is here on the right hand side. Therefore you would have, if you replace that, you would have 1 take away, and then this right hand side here, you can put that just in brackets. Get rid of the brackets, so it's going to be 1 take away. Well, you're taking away the x squared and you're taking away the negative, which means that's going to be plus 1/3 x to the power of 4, and so on. Remember, it's going to be infinite, so include your plus dot dot dot, and that there would be your cos squared x. Always remember, for your part B, you don't have to do the exact same thing for part A. You'd be there forever if you went through it again. Look for quick ways of doing it. If it was in an exam, it would only be worth 1 or 2 marks. They want something very quick. Woo! Example 7, find the Maclaurin series for the function f of x equals tan to the minus 1 of x up to and including the term in x cubed. So for this one here, again, it's the Maclaurin series, so you know you're going to have to differentiate. We want to differentiate our function. We want the first, the second, the third derivative. Differentiating tan to the minus 1 of x, does anybody remember what that would be? Well, if you look back to the differentiation chapter, if you're differentiating your inverse trig functions, differentiate tan to the minus 1 of x, and that was 1 over 1 plus x squared. So that is what you would have, 1 over 1 plus x squared, just from the differentiation chapter. So we need to then differentiate 1 over 1 plus x squared. How could we go about doing that? Brilliant. Move this up to the top line. If you move it up, you would have 1 plus x squared in brackets to the power of negative 1. That means we can easily differentiate that, bring the power down, keep the brackets as they are, take 1 off the power, and then multiply by the derivative of what is in the brackets. That'll be multiplied by 2x. Tidy that up, so you've got negative 2x multiplied by this 1 plus x squared to the power of negative 2, but you can move that down to the bottom of your fraction. So that is what you would end up with. That's the second derivative. We want the third derivative though, because we are looking for the term in x cubed. So to get the third derivative, how could you differentiate that? What could you do? Brilliant. Well done. You can use the quotient rule because you have a function in terms of x divided by another function in terms of x. So the quotient rule, if you have u over v, it will be u dash v take away uv dash over v squared. So u is going to be what is at the top. At the top here, we've got this negative 2x. At the bottom, we've got this 1 plus x squared, all squared. Differentiate both of them, so u dash will be negative 2. Differentiate v, so v dash will be, either you can multiply the brackets here because it's only squared, or you could just bring the power down, take one off the power, multiplied by the derivative. U dash v take away uv dash, that will become u dash times v. So I've got this 1 plus x squared in brackets squared multiplied by the negative 2. It doesn't matter which way around I write that. I'm taking away this negative 2x multiplied by the 2 bracket 1 plus x squared times 2x. But because I'm going to be taken away and I've got the negative, I could change that to a plus. And I've still got all of these parts. Divide that by v squared. So v is going to be the 1 plus x squared in brackets squared. If you square that, well, that's going to go to the power of 4. After that, well, all I'm doing is I'm tidying up this part here. I'm going to put that first because this part here on the left will work out to be a negative. So 2 times 2 is 4, multiply that by 2 is 8, and I would have an x times x, which is x squared. And I've still got this 1 plus x squared. I've got the negative 2, and I'm multiplying that by the 1 plus x squared all squared. So all I'm doing is just rewriting them the other way around. Start with the positive term, finish with the negative. And that's going to be over this 1 plus x squared to the power of 4. After that, look for common factors. You can take out a common factor at the top of 2 and the 1 plus x squared. So take them out as common factors and you'd be left with 4x squared. Take away just one of the 1 plus x squareds. Once you do that, you can tidy this part up. You've got 4x squared, take away 1, and you're taking away an x squared. So you've got 4x squared, take away x squared, which will be 3x squared, and we've still got this take away 1. After that, well, because you've got a 1 plus x squared in the top, and you've got 4 1 plus x squareds in the bottom, cancel 1 from the top, 1 from the bottom, so you will end up with 2 times by the 3x squared take away 1 over the 1 plus x squared to the power of, well, if you take one of them away, it'll go to the power of 3. And that there will be your third derivative. What do you want to do after that, after we have found this third derivative? Perfectly right. From there, after you have found the derivatives, you need to evaluate them all when x is 0. So, summary, this is what we have found. The first, the second, the third derivative. We now need to work out the f of 0 and f dash 0 and so on. So f of 0 tan to the minus 1 of 0 works out to be 0. If you sub 0 in here, you'd have 1 over 1 plus 0 squared, which is going to be 1 over 1, which is 1. This here works out to be negative 2 times 0 over, well, that works out to be 0 at the top, and 0 divided by anything is just going to be 0. And this one here, the third derivative, if you replace x with 0, you would have negative 2 times, that works out to be 0 times negative 1, so it's going to be negative 2 over, and then 1 plus 0 squared is going to be 1 plus 0, and that would just be 1 cubed, which is 1, so you've got negative 2 over 1, which is negative 2. So we've worked out f of 0, f dash 0, f double dash 0, and the third derivative when x is 0. We know once we have done that, we need to use the formula that is on the formula sheet for the MacLaurin series. So we can now replace f of 0, f dash 0, f double dash 0, and so on. So our function was tan to the minus 1 of x, inverse tan of x, equals f of 0 is going to just be 0, plus f dash 0 times x is going to be 1 times x. You're going to then have 0 over 2 factorial, so 0 over 2 times 1, which is 0 over 2 times by the x squared, and then you would have negative 2 over 3 factorial, 3 times 2 times 1, so it's negative 2 over 6, multiplied by the x cubed. Tidy that up and you end up getting x take away 1/3 x cubed, and that there is your answer. Example 8, give the first 3 non-zero terms of the Maclaurin series for cos 3x. And part B, write down the first 4 terms of the Maclaurin series for e to the power of 2x. And then C, hence determine the Maclaurin series for e to the power of 2x times cos 3x up to and including the term in x cubed. So first of all, we're going to be looking at the first 3 non-zero terms of cos 3x. So we would work out f dash x. So if you differentiate cos 3x, you end up getting cos will go to negative sign, 3x stays as it is, multiplied by the derivative, and that will be 3. So you get negative 3 sine 3x. Differentiate that, you would get the second derivative. So the negative 3 would just stay as it is. The cosine, if you differentiate that, you will get cos 3x will stay and multiply again by the derivative. Or you could differentiate negative sine and you get negative cos. Therefore, that tidies up to be negative 9 cos 3x. Third derivative, if you work that out, well, you would then have this negative 9. If you keep that just as it is, differentiate cos, you would get negative sine, so you'd have negative 9 times the negative sine, which means you would then have plus 9 sine. Keep the brackets as they are, and then multiply by the derivative, multiply by the 3. So you get 27 sine 3x. If you evaluate them when x is going to be 0, well, f of 0 works out to be 1. Because you'd have cos of 3 times 0 is going to be cos of 0, which is 1. Work out f dash 0, f double dash 0, and then the third derivative when x is 0, well, you'd have negative 3 times sine of 0. Well, sine of 0 is going to be 0, so it's just going to be 0 times something, which is 0. Here you'd have negative 9 times cos of 0. Cos of 0 is 1, so you just have negative 9. For the third derivative, 27 times sine of 0 is again just going to be 0. The problem with this, because we are wanting the first 3 non-zero terms, well, if you look at this, that will be a term, that'll be fine. But here, if you sub that into this formula, well, f dash 0 is going to be 0. So we'd have 0 times x, which is going to be 0, which means this term here will disappear. What we're asked for is the first 3 non-zero terms. So that there will be a non-zero term, but this term here will just be 0. This one here, if we sub it in, it'll be negative 9 over 2 factorial times x squared. So that's definitely not going to be 0. But this third one, again, is going to be 0. Because we'd have the 0 over the 3 factorial. It's just going to be 0. So we've only really got the 2 terms. So we need a third one. So keep on differentiating, get the fourth derivative. If you get the fourth derivative, you would get 27 cos 3x multiplied by 3, which gives you 81 cos 3x. Replace x with 0, so 81 times cos of 0 is just going to be 81 times 1, which is 81. You can now use this formula here, so you can replace f of 0, f dash 0, and so on. Doing that, and you end up getting f of x was cos 3x, f of 0 is going to be 1, this is going to be 0 times x, this will be negative 9 over 2 factorial multiplied by the x squared, that's 0 over 6, because that's 3 times 2 times 1, multiplied by the x cubed, and that is 81 over 4 factorial, 4 times 3 times 2 times 1 is 24, multiplied by this x to the power of 4, and so on. You can see from there that you do have some 0 terms. This works out to be 0, and this works out to be 0. So what it leaves you is with is 1, 2, 3 non-zero terms. So you'd end up being left with 1 take away 9 over 2 x squared plus the 27 over 8. That's what you get if you simplify 81 over 24, x to the power of 4. So that is the expansion for cos 3x. Part B, write down the first 4 terms of the Maclaurin series for e to the power of 2x. Well, doing this, you know if you're wanting to get the first 4 terms, you're going to have to differentiate. So work out the first derivative, the second derivative, the third derivative. We're wanting the first 4 terms, so the fourth term will be really your third derivative. We've got the first term here, then we'd have the second, then the third, then the fourth. Differentiate e to the power of 2x, well it stays as e to the power of 2x, multiply by the derivative, that'll be 2, so we'd have 2e to the power of 2x. Second derivative, 2e to the power of 2x would stay as it is, multiply by the derivative, so multiply by 2, and that will give us 4e to the power of 2x. Third derivative, keep the 4 as it is, keep e to the power of 2x as it is, but multiply by the derivative, multiply by 2, and we get 8e to the power of 2x. Evaluate each of them when x is 0, so we're going to have e to the power of 2 times 0. 2 times 0 is going to be 0, e to the power of 0, anything to the power of 0 is just 1. Because e to the power of 0 is going to be 1, it means it's going to be 2 times 1, so that will just be 2. This will be 4 times 1, and that works out to be 4. This here, replace x with 0, 2 times 0 is 0, e to the power of 0 is 1, so that's 8 times 1, so that works out to be 8. Again, we're going to be using that formula. This is your MacLaurin series formula. So f of 0 is 1, plus f dash 0 is 2, so it's going to be 2 times x. F double dash 0 is 4, so it's going to be 4 over 2 factorial, 2 times 1, which is 2, multiplied by x squared, so we've got 1, 2, 3 terms. We want the fourth term, so we need one more, which is why we need this third derivative. So that will give us 8 over 3 factorial, 3 times 2 times 1 is 6, multiplied by x to the power of 3. From there then, just tidy that up. 4 over 2 works out to be 2, and 8 over 6 works out to be 4/3. So that will be your answer. Part C, hence determine the Maclaurin series for e to the power of 2x times by cos 3x up to and including the term in x cubed. Again, Part B, Part C, Part D, normally they're all linked. For Part A, we had to express our cos 3x as the sum of a series, and for Part B, we had to express this e to the power of 2x as a series. For C, we're wanting the Maclaurin series for e to the power of 2x times by the cos 3x. So in other words, it's what we get when we multiply them together. You could always go down the route of using the product rule and then going through the Maclaurin expansion, but you would be there forever. The quick way of doing that is noticing just what I said. Really, this here is what you get when you multiply these two terms together. So if we multiply them together, we're multiplying the right-hand sides together as well. So we're just wanting to multiply them. So e to the power of 2x times cos 3x is going to be, well, e to the power of 2x works out to be, well, we've just got this here, and we're multiplying it by the cos 3x, which is this. So we're just multiplying both parts. You think that would take you forever if you did that, but notice the question is saying you're only wanting terms up to x cubed. So if you start multiplying them, well, you would have the 1 times everything. So we've got 1 times 1, which is going to be 1. We've got the 1 times the 2x, which is going to be 2x. We've got the 1 times the 2x squared, which is 2x squared. And we've got the 1 times the 4x cubed over 3. So we've multiplied everything by 1. We did the 1 times each of these. After that, we're then wanting to move on to the negative 9x squared over 2, and we're wanting to multiply that by everything. However, if you do that, we've got this negative 9x squared over 2 times 1, which will be negative 9x squared over 2. We've got the negative 9x squared over 2 times 2x, which works out to be negative 18x cubed over 2, because 2 times 9 gives you 18, so we've got the 18 over 2. We've also got the negative, and then x squared times x gives you the x cubed. But if you multiply this negative 9x squared over 2 by the 2x squared, well, you'd have an x squared times an x squared, which would be an x to the power of 4. That power is too large. We don't want that answer, so we don't need to write it. It's the same here. If we do the x squared times the x cubed, we'd have an x to the power of 5 term. Again, it's too large, so we don't need to do that. Moving on to the last term, if we take this one here, if we multiply that by everything, well, because there's an x to the power of 4, it's already too large. No matter what we multiply it by, the power is not going to decrease. So we don't need to do that. So that is all we would have if we multiply it together. That's all the terms up to our x cubed. Just put them together. We've got the 1. We've got the 2x. We've got a 2x squared. Any other x squareds? Well, we've got to take away 9x squared over 2. 9 over 2 is going to be 4.5, so 2 take away 4.5 gives us negative 2.5, which is negative 5 over 2x squared. And with the x cubed, we've got a 4/3 x cubed, take away 18/2 x cubed. Or you could think of that as 9x cubed. Doesn't matter which way you think about it, you could go with lowest common denominator. Doesn't matter how you do it, it works out to become negative 23x cubed over 3. That is just working out 4/3 take away 18 over 2. That there will be your answer. That is another 4 examples with the MacLaurin series. Slightly harder than the other lesson. That's 8 examples in total. Hopefully that is enough. Try these questions, see how you get on. Remember, the formula is here. It is given on the formula sheet. It's also in the booklet. You don't need to remember it. You just need to know how to use it. Best of luck. Try these questions, see how you get on. Have fun. Woo! Bye.